In this video, I will be discussing about exponential growth and exponential decay. Several phenomena in nature are so complicated that mathematics cannot be readily applied. At first, a lot of observations and experiments will be made in order to arrive at a testable theory. Afterwards, mathematics is then applied in order to model the phenomenon approximating the real situation in this physical world. Actually, mathematicians and physicists noticed that many physical laws they have derived from this procedure are represented through the use of differential equation of order 1. So at this point, some of the physical applications will be presented in a form of differential equations where its role is very important. So here, I will be discussing about the law of exponential change. And the law states that the time rate of change of the quantity n at a time t is proportional to its amount n. And there will be two types of these processes which will be considered here: the exponential growth and the exponential decay. So, if n represents the number or amount of a certain substance which behaves according to the law of exponential change at any time t, then this can be written as the rate of change in n with respect to time is proportional to its amount n, and we refer this one as our equation 1. Now take note that k here is a constant of proportionality. Then solving equation 1 by separating the variables, we have this equation 1 as the differential of n over differential of time, which is proportional to the big N. We can separate all n's to the left and all terms without n to the right by multiplying both sides of the equation by dt here. So multiplying dt, we have the differential of n over 1, because the dt here will be cancelled, is equal to kn times dt. And since we want the big N to the left to group them as 1, we need to multiply both sides of the equation by 1 over the big N. So we have the differential of big N all over big N is equal to k dt. And since we have separated the variables, we can take the integral of both sides. And we know that the integral of dn over n is the natural log of n. Then we can also take the integral of k dt, where k is a constant, so the integral of dt is t plus some constant, say c prime. And converting this one to its equivalent exponential form, then the natural log of n, which is equal to kt plus c prime, where this right hand side is the exponent of the base of this natural log of n, and the base of this natural log of n is equal to the Euler's constant e, and this should be raised to this exponent kt plus c prime, which should be equal to our big N. And applying the laws of exponents, where the exponent is a sum of two quantities, this can be decomposed to e to the power kt times e to the power c prime. And you can check by the laws of exponents that when you multiply this, you can just add the exponents here, which is equal to this one. So we write this one as the big N, which is equal to e to the power kt times some constant c, because the constant e is raised to another constant c prime. The result is still a constant. So we write this one as a constant c. So we write here where c is equal to e to the power c prime. And because this is a constant, we can write this one before this exponential notation. So our big N is equal to c times e to the power kt. Then therefore, this is our exponential equation. And we represent this one as our equation 2. So this is now the exponential equation of a phenomenon that behaves according to the law of exponential change, where the big N is the total amount and c together with the k are all constants. Now, we have two remarks here describing our equation 2. Since the big N in this equation 2 is expressed into three unknowns, namely c, k, and t, then there must be two known boundary conditions like c and k in order to express our big N as a function of time t alone. Number 2, that in this equation 2, if k is greater than 0, meaning positive, the process is called an exponential growth. And if k is less than 0, in other words, negative, then the process is called an exponential decay. So to give you an application of this equation, then example 1. The population of a certain community follows the law of exponential change. If the present population of the community is 144,000 and 10 years ago it was 100,000, then find the expression for the population size n as a function of time. So here we can use our exponential change formula, which is this one here. So the big N is equal to c times e to the power kt, where n denotes the population size of the community at any time t. Now, it was given in a problem that the present population of the community is 144,000, then we can write here that when t is 0, meaning at the start, our population size is equal to 144,000 here. Then we can write our big N as 144,000. So 144,000 is equal to c times e to the power of k times 0. And k times 0 is 0. And we know that when the exponent is 0, whose base is a non-zero constant, then it is equal to 1. So this is equal to c times 1. Therefore, our c is equal to 144,000 here. Thus, our formula becomes the big N is equal to c, which we know that this is equal to 144,000 times e to the power of kt. However, it was also given in the problem that 10 years ago, the population size was 100,000. So, we can write here that when t is equal to negative 10, then our n is equal to 100,000. So, then this is our second boundary condition. Now, substituting these boundary conditions here, we have our n as 100,000, which is equal to this 144,000 at the start times e to the power k times the time of -10. Why -10? Because this was 10 years ago. And dividing both sides of the equation by 144,000, we have 100 over 144. And this is equal to e to the power -10k. Now, reducing this one to the lowest term, we have 25 over 36, which is equal to e to the power -10k. So, converting this exponential notation to its equivalent logarithmic form, we have the natural log of our 25 over 36 is equal to the -10k. And dividing both sides of the equation by -10, we have the natural log of 25 over 36 divided by -10 is equal to k. And solving for k here, using a calculator, we have k which is equal to 0.0365. Then therefore, we can say that our population big N is equal to 144,000 times e to the power of 0.0365 t. And this is our population formula as a function of time t. Now let's proceed to the second question here. Find the time t when the population size will be doubled. And when the population size will be doubled, our big N is equal to 288,000, which is twice of this 144,000. So writing this formula, we have 288,000, which is equal to 144,000 times e raised to the power of 0.0365 t. So dividing both sides of the equation by 144,000, we have 288,000 divided by 144,000, and the quotient is 2. So this is 2 equals e to the power of 0.0365 t. So converting this one to its equivalent logarithmic form, we have the natural log of 2, which is equal to 0.0365 t. And dividing both sides of the equation by 0.0365, we have the natural log of 2 divided by 0.0365 is equal to our time t. And solving for our t, we have the quotient, which is approximately equal to 19. So the number of years that the population size will be doubled is 19 years. So this is the time needed for the population to be doubled. Now let's proceed to the third question here. What will be the population of the community in 10 years to come? So here we will substitute when t is equal to 10. So we have big N, which is equal to 144,000 times e to the power of 0.365 times t, which is equal to 10 years. So big N is equal to 144,000 times e to the power of 0.365. And using your calculator, e to the power of 0.365 is equal to 1.440514008. And multiplying this one to 144,000, we have 207,434. So this is our population size in 10 years to come. Now let's proceed to our example number 2 here. A certain radioactive material is known to decay at a rate proportional to the amount present. If after 1 hour it is observed that 10% of the material has decayed, then find the percentage remaining after 5 hours. So first, let us model this decay using our exponential change equation, which is equal to big N, which is C times e to the power kt. Now, at this time, let us represent n naught or n sub 0 as the initial amount or the initial quantity. So in other words, we say that n sub 0 at time 0. So we have n sub 0 is equal to c times e to the power k times 0. So our time is 0 because that is the initial time and the amount was n sub 0. So multiplying 0 to k, we have e to the power 0, and e to the power 0 is 1. So our c is n sub 0 here. So our formula becomes n is equal to n sub 0 times e to the power kt. But it was given in the problem that after 1 hour, the material has decayed 10%. So we can write here that after 1 hour, which means t equals 1, our amount of the material is equal to 90% of the initial amount. So rewriting this one in decimal form, we have n, which is equal to 0.9 of our n sub 0. Because remember, the material has decayed 10% after 1 hour. So the remaining amount is 90% of our initial amount, which is n sub 0. Since n sub 0 is the representation of our initial amount. So this formula can be written as 0.9 of n sub 0, because this is our big N after 1 hour, is equal to n sub 0 times e to the power k times 1, because that is after 1 hour. So dividing both sides of the equation by n sub 0, n sub 0 will be cancelled. So 0.9 is equal to e to the power k. And converting this exponential notation to its equivalent logarithmic notation, we have k, which is equal to the natural log of 0.9. And using your calculator, the natural log of 0.9 is equal to the negative of 0.10536. Thus, our formula, which is this one, can be written as big N, which is equal to n sub 0 times e to the power of negative 0.10536 t. So this is our formula for this exponential decay here. And you notice that in solving this formula, we need two boundary conditions. The first boundary condition is the initial amount at time 0. And the second boundary condition is after 1 hour. Now, answering the first question, find the percentage remaining after 5 hours. So here, our t is 5. So when t is 5, then we can substitute our t here. Big N is equal to n sub 0 e to the power negative 0.10536 times 5. And using our calculator, we have n sub 0 times e to the power of negative 0.5268 here. And solving for e to this power, we have n sub 0 times 0.5905. So our n is equal to 0.5905 of n sub 0. So therefore we say that after 5 hours, the remaining percentage is 59.05% of the initial quantity or initial amount. And finding the time that it will take for the material to decay 30% of its original amount, we write mathematically that our n is equal to 0.70 of the initial quantity because it has decayed 30%. So what is remaining is 70% of the initial amount. And substituting this one to our formula, we have 0.70 of n sub 0 is equal to n sub 0 times e to the power of 0.10536 t. And dividing both sides of the equation by n sub 0, what will remain at the left is the 0.7, and this is equal to e to the power of negative 0.10536 t. And rewriting this one in its equivalent exponential form, we have the natural log of 0.7 is equal to negative of 0.10536 t. So dividing both sides of the equation by this negative 0.10536 here, we have t, which is equal to the natural log of 0.7 divided by negative 0.10536 here. So t is equal to 3.39 hours here. So this is the time required for the radioactive material to decay 30% of its original amount. Now finding the half-life of the material, which is the time required to decay half of the initial amount, we can write in mathematics that our big N is equal to half of the original amount or initial amount. So substituting this one to our formula, we have 0.5 of n sub 0, which is our value of n, is equal to n sub 0 times e to the power of negative 0.10536 t. So dividing both sides of the equation by n sub 0 will be cancelled. So we have 0.5, which is equal to e to the power of negative 0.10536 t. And rewriting this one to its equivalent logarithmic form, we have the natural log of 0.5 is equal to negative 0.10536 t. And dividing both sides of the equation by this negative 0.10536, we have our t, which is equal to the natural log of 0.5 divided by negative of 0.10536. So t here, by using a calculator, we have 6.58 hours. So this is the time required for the radioactive material to decay 50% of its original amount. In other words, it will take 6.58 hours to decay half of its original amount. And that's it. If you learned something today, please check out my channel for more videos like this and click subscribe. Click the notification bell below so you'll get notified whenever I'll be posting a new video. Don't forget to like this video to show your support. And always remember to math your way up. Thank you.